Today we're going to have a short video about John Dalton. John Dalton was the one who came up with the explanation, the theory behind these two mysteries that we had at the end of our last video. One of the mysteries was called the law of definite proportions, which says that the ratio of the masses of elements in a compound is always the same. It's consistent. It's a definite proportion. And we saw it in this example. We had a compound A here. We had three different samples of it, and we found that every time we divided the mass of sulfur by the mass of oxygen, we always found this particular ratio. It was about 1. 1.001 we got, 1.0008, and then we also had a 1.01. But it always was really close to 1. Then the second mystery was called the law of multiple proportions. And the law of multiple proportions says if you had two compounds and you found that definite proportion for both of those compounds, and you took the ratio of one of them to the other one, you would get a small whole number ratio. And this was inexplicable. Here's an example. Compound A that we just had, the average sulfur to oxygen ratio is 1.001. If we did compound B, which is also made of sulfur and oxygen, we found that ratio and it came out to be 0.6689. Then if we make a ratio by dividing the definite proportion in A, which is 1.001, by the definite proportion in B, which is 0.6689, we find out that we come out to around 3/2, or if we had done it upside down, it'd be 2/3. It was always coming out that way, 2/3, 3/4, 1/2, some kind of simple, like a fourth grade fraction. No explanations for this yet, but it always kept happening, and so it became called a law. Well, here's the person who finally came up with an explanation. His name was John Dalton. John Dalton lived in the late 1700s, early 1800s. He didn't have a college education because he was a Quaker, and Quakers were not allowed to go to college, to university, because the university was controlled by the Church of England at the time. But he was very, very smart, and he sort of taught himself. And by the time he was 12 years old, he became a teacher. He taught high school, essentially what we would call high school, and he also was a lecturer. Back in these days, people didn't have that much to do to entertain themselves, and they were actually interested in learning about the world. And so a person like John Dalton could go around and make a little cash by delivering lectures, giving speeches about things that he knew. And by the time he was 12 years old, he was doing that for a living. He was that smart. Well, he was really interested in meteorology, and he kept reading about things, discoveries that might help him understand how gases in the air would behave in meteorology. And he kind of stumbled onto this idea that helped explain things. It's called the atomic theory. He kind of went back to Democritus and Lucretius and borrowed some of their ideas, but with the understanding of Lavoisier that everything is made of a limited number of elements. So Dalton's atomic theory, we're going to explain it in a few postulates or statements. The first postulate is all matter is made up of tiny, indivisible atoms. So nothing new here. This is also what Lucretius and Democritus believed and had been forgotten for centuries. So everything is made of these little bits of matter, and you can't divide them into anything smaller. The second postulate is atoms of one element are all the same as each other. Atoms of another element are all the same as each other, but atoms of different elements are never the same as those of the other element. In other words, atoms of different elements are always different. So here's what we're looking at here. Let's say we have oxygen and sulfur. All oxygen atoms are going to be the same. They're going to weigh the same. They're going to be the same color if they had a color. They're going to be the same shape. Everything about them is going to be identical. Sulfur atoms are all going to be identical to each other. But there's no sulfur atom that will ever look like an oxygen atom or have the same mass as it or any other characteristic. You can't create or destroy or change any atoms. So it would not be possible for me to come up with new sulfur atoms that didn't exist before. They would have to have already been there. I could also not get rid of an oxygen atom, for example. You can't destroy them. And another thing that wouldn't be possible would be I couldn't change an oxygen into a sulfur or a sulfur into an oxygen. Atoms couldn't be created, destroyed, or changed. That's part of his theory that would help explain why matter behaves in these multiple proportion and definite proportion ways. And so here's what this means, and here's our last postulate. A chemical change is really only a rearrangement of atoms. When chemical change takes place, the same atoms are there before and after the change. They're just rearranged, put together a different way. So compounds really are just different combinations of identical atoms. Here's one compound made of sulfur and oxygen. Here's another compound made of sulfur and oxygen. The difference between these compounds is, well, this one just has more oxygen atoms for every sulfur. Now this explains both of these laws. It explains the law of definite proportions in this way. If I have a sample of just one molecule of, let's call this compound A, well, I have 2 oxygen atoms for every 1 sulfur atom. Here's another sample. I've got 2 clusters, molecules is what we call them nowadays, of sulfur and oxygen atoms, and they're the same compound, so they're put together the same way. And so what do I have? I've got 4 oxygens for 2 sulfurs. But really, I can reduce this, and this is really 2 oxygens for every 1 sulfur. And here's another sample where I've got 3 of these clusters, which means I've got 6 oxygens for 3 sulfurs. But that reduces again down to 2 oxygens for every 1 sulfur. And if all oxygen atoms weigh the same, and all sulfur atoms weigh the same, it doesn't matter if I have a tiny sample or a huge sample of this compound. It's always going to reduce down to 2 oxygen atom weights divided by 1 sulfur atom weight. And so that's why you always get the definite proportions. It seems obvious to us today because we're so used to atomic theory. Atomic theory has permeated how we understand matter. It's that important of a theory. But in Dalton's day, this was really a revolutionary idea. Here's how it explains the law of multiple proportions. Here's compound A that we were just looking at, and we've seen that you have 2 oxygens for every 1 sulfur. Well, here's compound B. In compound B, we can see there's a different arrangement. We've got 3 oxygens for every 1 sulfur. Now, if I were to take a whole bunch of compound Bs and weigh their oxygens and weigh their sulfurs, I'd get some definite proportion based on how much oxygen and sulfur weigh. But the oxygen atoms in compound B are the same oxygen atoms that are in compound A. Same size, same shape, same weight. And the same thing is true for the sulfur. So if I take a ratio of definite proportions, here's what I'm really doing. 3 times the weight of oxygen divided by 1 times the weight of sulfur for compound B divided by 2 times the weight of oxygen over 1 times the weight of sulfur for compound A. So here's compound B on top, and here's the definite proportion for compound A on the bottom. Well, when you cancel out the mass of sulfur, which is going to be the same on top and bottom, you have 3 times the mass of oxygen divided by 2 times the mass of oxygen. But the oxygen atoms are the same in both compounds, and so that just cancels out. And there's your multiple proportion, 3 over 2. So Dalton's theory explains both of these mysteries that nobody had an explanation for. And it does it so thoroughly that it became a permanent part of our understanding of the world. And I don't think it will ever go away. Now, Dalton wasn't right about everything. The indivisible part turned out not to be true. And we're going to look at some advancements in science that came after Dalton. But the basic idea is going to endure for a long time.